Hello. So, we have discussed some techniques how to solve 2-point boundary value problems. For example, finite difference methods, both linear, non-linear, and then also shooting methods. Okay. So, let us have some problems using these techniques. Okay. So, especially we try to solve some problems explaining the concepts of finite differences. Okay. So, let us do that. On BVPs. Okay. See, we have been solving a lot of examples, but can we get some real life example or practical example where finite differences could be used? So, in particular nonlinear. So, simple pendulum. So, I consider this example. So, you have simple pendulum. Okay. So, this weight is mg. So, this is the initial configuration when theta is 0 and this length is L, let us say, and this is theta. Okay. So, I do not want to explain the physics behind it, because you can derive balancing the forces, one obtain d square theta by dt square equals minus g by L sin theta. So, this one can call k sin theta. Okay. So, as BVP, if we would like to define this is k. So, this is where the nonlinearity in the dependent variable, t is independent variable, and the boundary conditions theta of 0 is alpha. So, say some pi by 4. Okay. Then say theta of at any time, at time t 0, let us say we have released at an angle. Okay. So, then at some other time b. So, this we want to given some other time, it must be beta. Okay. So, this can be defined as boundary value problem, and if we discretize, we end up with discretizing star, we get nonlinear system that can be solved using NR method. Okay. So, this is one example I would like to mention. Then grid refinement. Okay. So, another is grid refinement. Assume that a method is of order p. Okay. So, then we have seen the error with a specific h is bounded and it is behaves like this. Okay. Suppose we divide h by half, then what would happen? This with h by 2 c times h by 2 power p, assuming the same constant. Okay. So, then the ratio Okay, this goes like h by 2 power p. So, this is 2 power p. Okay. So, this ratio is 2 power p. Okay. Moreover, this is log C plus p log h. Then we can solve for p in terms of the ratio. Okay. So, now if p is 1, ratio is 2, p is 2, ratio is 4. So, this give an idea on if we refine the grid, how the error and then compared to the earlier h, the ratio of the errors, how they behave. Okay. So, accordingly, without recalculating, one can get some estimates. Okay. Right. So far, whatever examples we have discussed, or while delivering lecture as well, many of the examples many times in the books, they are given in terms of Cartesian coordinates. Okay. So, let us look at a slightly different problem. Okay. So, I would like to write down completely, so that we literally in a better position. Consider a pressure vessel that is being tested in the laboratory to check its ability to withstand pressure. So, there is a vessel. Okay. So, in this case we are going to define it, it is a circular, and it is being tested to check its ability to withstand pressure for a thick vessel of inner radius A and outer radius B the differential. So, you can consider some tube. So, inner radius A, outer radius B, this is a tube and we are testing the pressure. Okay. So, the differential equation for the radial displacement u of a point along the thickness is given by So, that means okay. So, the radial displacement along the thickness. Okay. So, it is just function of r, right, radially, because we are testing for the pressure. So, the radial displacement. So, it is a tube kind of thing. Okay. So, it is governed by this equation, and let us say A is some 5 units, B is 8 units, and given u at r equals to A is some value and u at r equals to B, okay, right. Solve for u at intermediate nodes by dividing the radial thickness into 6 nodes. Suppose this is a kind of application. Okay. What I would like to mention is it need not be every time we are in a Cartesian framework. So, this time we are in a radial framework. Okay. So, now, so this A to B, this distance, okay, we have to cut it into 6 nodes. Okay. So, let us discretize. So, discretizing we get so instead of h, since it is radial coordinate, I am using the increment delta r square. Okay. So, this is u I by r square. So, now this can be written by collecting the coefficients. Okay. And delta r b minus a by 5, 6 nodes. So, 5 intervals. So, this will be 0.6. Okay. I equals to 0, we have r 0 equals to a equals to 5, and the corresponding u 0 is, then I equals 5, r 5 is 8 and u 5 is okay. So, now intermediate values we write I equals to 1, r 1 is 5.6. Then we simplify the coefficients, and write a system. So, I equals to 4. Okay. So, we can solve, or this is a tridiagonal system. So, we can obtain u1, u2, u3, u4. Okay. So, this is some sort of application where we do not have always radial coordinate. So, we have we do not have Cartesian coordinate, we have a radial coordinate. Okay. Show that the central difference method for y double equals to f of x with Dirichlet boundary condition is second order accurate. So, that means show that the central difference method used for this with the Dirichlet boundary condition is second order accurate. So, that means we have to show that the error is second order. Okay. Right. So, if we use central difference, okay, we get this. Then if we put it in the matrix form, the matrix A will be okay. So, then here so this is our A. So, this can be put in the form okay, where so this matrix n minus 1 cross n minus 1. Okay. Then we have y 0 is some gamma 1, y n is gamma 2. These are the Dirichlet boundary condition, because no derivatives are involved. Okay. Now, so the eigenvalues of A are lambda j so this is so these are the eigenvalues. Okay. Then the eigenvalues of A inverse are 1 over lambda j and A inverse is symmetric. So, therefore, the 2 norm I have given in one of the lectures. Okay. So, you may refer. For the error to be bounded, there is a condition, I have stated a condition, the A inverse, the norm of A inverse must be bounded. Okay. So, this with 2 norm, okay, it will be this. So, this is h square okay. So, this can be shown to be pi h pi h square by 2 plus pi h 4 by 4 factorial. So, minimum we take it. So, this is pi h. So, this okay, this can be shown to be bounded. So, therefore, the error with 2 norm, this is actually this is we have obtained in okay, times h square second order accurate. So, this is the what when p is the method. So, in this case, so it is not therefore. So, we have this, but in this case this is this and we are getting h square. So, the total this implies is less than or equals to some c times h square. So, therefore, it is second order accurate. Okay. So, one can check accordingly the accuracy of the methods. Okay. So, this example will give impact of approximation on the solution. So, consider okay. So, this can be thought of as one dimensional diffusion equation. Okay. So, in the context of convection diffusion, the k has a specific meaning. Any case, dropping that, at least this can be thought of as an application to convection diffusion problem. Okay. So, now we would like to discuss the impact of approximation on the solution, right. So, case A, approximating both the derivatives using central. So, if we do that, okay. So, this can be put it in the form So, we get the following difference equation. Okay. Then the characteristic equation is given by this. The roots so, the roots are this, hence the general solution is given by y n is C 1 1 power n, C 2 n. Okay. So, this is a general solution. Okay. So, we need to obtain the conditions for stability, because what is the use? We are trying to discuss impact of approximation on the solution. So, for the central we obtained this, and this is a solution. Okay. So, this is C 1 plus C 2 2 k minus h. Okay. And analytical solution, that means the exact solution Okay. So, if you look at this, so this is the disturbance and is how it is growing. So, we have to discuss the growth of the disturbance. Okay. So, if mod is less than, then we get stable solution. Otherwise, this would grow. Okay. If mod 2 k minus h is greater than 2 k plus h. Okay. Of course, so this is one condition. So, now let us look at B. If y dash is approximated by forward, then of course, y double prime usual central, so then this implies so the characteristic equation and the roots are okay. So, therefore, the general solution is So, this is a general solution. Okay. So, this is okay. So, now k greater than 0, k greater than 0. So, let us check the roots of this equation. So, I think these are the correct. Okay. So, this is these are the roots, and then this is the solution. So, k greater than 0, if k greater than 0, then we get conditional stability. So, what should be the condition? If k is greater than 0, we should get, see, essentially we should obtain the condition mod 2 k plus h must be less than mod k. So, then we get the stable solutions. So, this is a region we should try to get. So, this implies we may get minus 2 k. Okay. Then k less than 0, we get stable unconditional, and k is less than 0. Okay. So, k is much smaller than 1, it is highly infeasible because it grows. Okay. So, this is the impact of the differences approximation. C y dash d is approximated by backward. Okay. So, this will be and the characteristic equation is and the roots are. So, therefore, the solution, general solution is C 1 plus C 2 1 minus h by k power n. Okay. So, therefore, k greater than 0. So, this will be unconditional stable. Okay. K less than 0, we must get the condition. Okay. If k is less than 0, so then we must get k has to be larger than h. Okay. Modulus of k. So, this is the conditional stability. Okay. Okay. So, let us proceed further with few more examples. Undetermined coefficients method to determine finite difference formula. Suppose one would like to obtain one-sided finite difference approximation to y dashed x at say x equals to b, which is the boundary. Okay. Using, so one sided means, see this is x equals to b. So, one sided means does not involve one of the sides. So, either this side or this side. Okay. So, using in this case to second order accuracy. Okay. So, what is our aim? To obtain y dashed x approximate up to second order in terms of one sided, all terms to the left side. Okay. So, that means y I prime is alpha y I beta y I minus 1 plus gamma y I minus 2. It must be of this form. Okay. Right. So, we have to now determine undetermined coefficients. So, we have to determine the coefficient such that this approximation is second order. So, what do we do? Use Taylor's expansion. Okay. So, by doing this is alpha y I beta y I minus 1 gamma y I minus 2. So, this alpha y I beta y I minus h y I prime plus h square by 2 y I double plus gamma y I minus 2 h, this is y I minus 2. So, 2 h plus order of maximum of mod alpha, mod beta, mod gamma, h power 4. So, the remaining. Okay. Now, double star must approximate y I prime up to second order. Okay. So, up to second order this must approximate. Okay. So, let us force the coefficients up to second order. Okay. So, from here, so we need up to second order approximation, right. So, y I alpha plus beta plus gamma is 0 and y I prime right hand side minus beta h, then here minus 2 h gamma and right hand side 1. Okay. Then squared here beta h square by 2 and here h square by 2 gamma and there is nothing. Okay. So, now on solving we get alpha is 2 by h, beta is minus 2 by h, gamma is this. So, therefore, we get the approximation 3 by 2 h y I minus 1 okay. So, an exercise for you, obtain so obtain L in. So, that means you have to determine this. So, you can see in this case suppose this is x. So, this is one sided, but the right hand side it is considered. Okay. Right. So, this is very similar to what we have done. Okay. So, now I guess example 7. Let us talk about symmetric boundary conditions. Suppose we have the following problem, y dash of 0 is 1. Okay. So, if we discretize, suppose the condition is this. Okay. Suppose if we discretize y dash of 0 is 0, this implies y 1 equals. So, this is posing symmetry. Okay. So, here it is y 0. So, now this is symmetric case. Okay. So, now if we discretize and the characteristic equation. And the roots are and this is so one can approximate this by series expansion. Okay. So, therefore, the general solution is so this is the general solution. Now, the symmetry y 1 is y minus 1. So, this implies C 1 E h okay, y 1 minus 1 so this is minus here. So, this implies C 1 equals to C 2. Okay. So, that means when we have symmetry boundary condition, okay, suppose this is 0. So, this is x 1, x minus 1, x 2, x minus 2. So, the correspondingly so if we have symmetry boundary conditions, then it is enough to solve the values at grid points lying on one of the sides from the point of symmetry. So, for example, we can solve here or we can solve here. Okay. Yeah. So, let us look at derivative boundary conditions. So, minus 1 and h is 1 by 3. So, usual discretization okay. Right. So, now usual discretization right. So, we have so 1 over h is 3. So, 1 over h square is 9. So, we have 9 minus 18 y I so we have minus x I plus 9 y I so this must be run from I 0, 1, 2, 3. The reason is we have derivative boundary conditions. Then so this will be y 1 minus 1 by 2 h. So, y 0 is 1. So, this implies y minus 1 equals y minus 1 equals y 1 okay. So, this is y 1 plus 2 by 3 y 0 minus 1 and the other one we have y dash 1 is minus 1. So, this implies y 4 is y 2 by 2 h minus 1. So, this implies y 4 is so we have two fictitious values, then we run the equation 0, 1, 2, 3. So, we get 4. So, the how many unknowns? So, two fictitious values will come. So, they will be eliminated. So, 4 equations in 4 unknowns. Okay. So, if we run this, for example, I 0 implies 9 y minus 1, x 0 is 0, y 0, y 1. So, we have then y 1 minus 2 x 1 plus 9. So, where are the fictitious values? And with already we have computed. So, we substitute so using A and B in sys, say this is sys. We get a tridiagonal system. Okay. So, one can solve. Okay. So, these examples I am sure would place you little comfort. because we have covered a variety of issues, grid refinement and derivative boundary conditions, error calculation and several aspects. For example, how to obtain a difference scheme like undetermined coefficients. Okay. So, this keeps you definitely little comfortable, so that you can attempt any problem covering finite difference methods. Okay. So, let us look forward for moving further. Until then, bye bye.